Chapter 2, Section 3 is relatively short. It has to do with atomic symbols, some of which you've seen before, probably just in everyday life. But the symbols are a shorthand, internationally accepted way that we can represent the subatomic particles in an atom in one tight, compact unit that in a language that everybody speaks, internationally accepted. So the atomic number, which is abbreviated with a capital letter Z, I do not know why. I suspect it's from German. Before World War II, a lot of chemistry was written in German. Then after they lost World War II, English. But even when I was in graduate school, if I was looking up a really old chemistry paper, it was in German and I needed to get somebody to translate it. Anyway, the atomic number, which is a preceding subscript before the symbol, okay, the symbol is just represented by a generic X here, that represents the number of protons in the nucleus. If it's a different number of protons, it is a different element. We now know that the number of protons in the nucleus is what defines an element. If it's got 6 protons, it's carbon. If it's got 7 protons, it's nitrogen. If it's got 8 protons, it's oxygen. If it's got 7 protons, it is not carbon. It is not nitrogen. It is nitrogen. Okay, that's the definition of an element as it stands now. The mass number, which is a preceding superscript before the symbol to the left of the symbol, is the number of protons plus the number of neutrons, and that can vary for a single element. There's carbon 12, there's carbon 13, there's carbon 14. Most of the carbon in your body is carbon 12. Carbon 14 is what's used for radiocarbon dating things, which you may have heard of on TV. Those different isotopes of carbon vary in their number of neutrons, not the number of protons, because that's a different element. Okay, just another example. Here are some common isotopes of hydrogen. This is regular old hydrogen. Most of the hydrogen in the universe is hydrogen 1, with 1 proton, atomic number, no neutrons, because its mass number is also 1. Deuterium, so common in chemistry discussions that they gave it its own fake element symbol, D. All right, that's not a real element on the periodic table, but they've given a capital D as the symbol for deuterium. That is hydrogen 2, still mass number of 2. So that's how you pronounce this, is hydrogen 2. Mass number of 2 because it has 1 proton, okay, atomic number of 1, and it has 1 neutron. Heavy water is D2O or T2O or HDO or HTO or DTO. Heavy water is water that contains some deuterium or tritium. Tritium is the fake symbol name that we've given for hydrogen 3. Still atomic number 1 because it is hydrogen with a mass number of 3, 2 neutrons. Okay, these 2 neutrons are picked up naturally or artificially in a nuclear reaction. The symbols here just show 1 proton in the nucleus, 1 proton and 1 neutron in the nucleus. Are they really red and green? No, that's just our representation of it here. 1 proton and 2 neutrons in the nucleus, okay? With 1 electron flying around the outside of it that is not shown. Uranium, used in nuclear medicine, nuclear weapons, and nuclear power. It has quite a few common isotopes. Uranium-235, uranium-238. I'm pretty sure 235 is what's used in weapons, but I don't remember off the top of my head. In any case, notice atomic number 92, atomic number 92. Both atomic number 92 because they are both uranium. This one has 235 minus 92 neutrons. This one has 238 minus 92 neutrons. Got it? And you can do that math on your own. Now, remember that atomic symbols, some may make sense, some may not make sense based on the English language. If you watched this joke in an earlier video, then you already know that when 16 sodium atoms walk into a bar with Batman right behind them, that joke makes total cheesy sense because you have Batman. Okay, sodium is Na from natrium. You may have heard of natrium because every once in a while on the side of a bottle of shampoo or in a commercial, they'll say infused with natrium. Don't buy this product because they're trying to impress you. and it means salt added because they've added sodium, and you can't have sodium by itself because sodium in water explodes, so it probably comes with something else, and oftentimes the cheap way to add sodium to something would be as the chloride, sodium chloride, or maybe sodium sulfate, or some other sort of sodium lauryl sulfate shampoo. In any case, infused with natrium, they're trying to make it sound fancy. They just mean that it's got sodium atoms in it, probably as sodium chloride. Question for you. Radiocarbon dating, again, uses carbon-14. How many neutrons does this radioactive isotope have? I will stop the recording and you can enter your answer. Okay, 14 minus 6, the atomic number of carbon, right? 6 is its atomic number. C has to be here, okay? It's kind of redundant, so oftentimes the 6 won't be here. When you're doing nuclear reactions, balancing nuclear reactions, you absolutely want to include the atomic number because it makes balancing nuclear reactions trivial, just super, super, super easy. We won't do it this semester, but it is super easy. However, just when we're first starting out, we will include the atomic number, but it is redundant, and chemists are lazy. We don't like to include redundant information. This has to be 6C, because if it was 6N, it wouldn't make any sense, because N needs a 7 there. N is atomic number 7. 8 here would have to be an O. So since it's redundant, most of the time we omit the atomic number, but the mass number we must include because we can have these different isotopes that vary in their number of neutrons. So 14 minus 6 is 8 neutrons in carbon-14. Just some more atomic symbol humor for you here. The elements' names were internationally agreed upon over time, and so they some of them have changed over time. They got some finalists for the names, and then they tossed them out. So if you're interested in periodic table history, there's a lot of it out there available, but this one from Compound Chem, this poster, if you click on it, links to the some of the more common names that have changed over time. Okay, if you have an atom that contains 30 protons, 30 electrons, and 35 neutrons, so it's a neutral element, right? It's got just as many pluses as minuses, which is how, I'm not going to say how elements come, but if we're just talking about elements on the periodic table, not necessarily in nature or anything, a neutral element that nothing has happened to, no chemistry has occurred on, then we're talking equal numbers of protons and electrons. There's balance. You may have heard that there's chaos in the universe and the disorder is expanding. That's true. Law of thermodynamics, entropy is increasing. However, this is one case where there's things in balance. All right, equal numbers of protons and electrons when no chemistry has occurred. Regardless, if it's got the 30 protons and electrons and 35 neutrons, what is its mass number? I'll give you choices, and you can enter your answer. All right, so 30 protons, 30 electrons does not, and 35 neutrons does not add up to 95, okay, because the mass number does not include the electrons. They don't weigh anything. They're effectively massless. So we're only talking about the things that lead to the mass of the atom, which is all the stuff in the nucleus, the protons and neutrons, so that is 65. 4 more questions for you here, although D you've pretty much already done, but let's do number of protons, neutrons, and electrons in each of the following. I will pause the video and you can enter your answers. Okay, so let's do it here. We'll make a little handy-dandy chart. And if I can find the cursor, here we go. All right, so let's do protons, electrons, and neutrons for these guys, okay? All right, so sodium is atomic number 11, so that's the number of protons. It defines the element. There's no charge. This is where the charge would be written, okay? A plus or a minus if chemistry had been done to it, but none of these have any charge, so no chemistry has been done to these things. So there are equal numbers of protons and electrons, so 11 electrons for sodium, 20. Number of neutrons, 20 minus 11, sodium 20 has 9 neutrons. Sodium 22, 11 protons, 11 electrons again. 22 minus 11, sodium 22 has 11 neutrons. These two isotopes differ in the number of neutrons. Sodium 20, 9 neutrons. Sodium 22, 11 neutrons. Oxygen 17, notice, the atomic number is omitted. That's fine, it's redundant anyway. If it's oxygen, it is atomic number 8. Look at the periodic table. No chemistry has been done to it, so equal number of protons and electrons. And 17 minus 8, 9 neutrons in O17. O18 was one of the first things that I used when I was in college. As a sophomore, I was doing research, and the first day I got to the research lab, the professor came to me and handed me this little crack vial of white powder and said, this is O18 labeled urea. So it was 1989. Costs $1,000 a gram. Don't spill any. And I got really good at being really careful, really fast in his lab. All right, carbon-14. You may remember that's one way of writing it. The other way that we had it before was carbon-14. Right? The 6 down here would be redundant, but we could put it there if you want. So that means that it has 6 protons and 6 electrons. And 14 minus 6, carbon-14 has 8 neutrons. All right. I do have the solution on the next slide, but I don't know that you particularly need it. I'll leave it up here if you want to freeze frame it, but we already discussed it. And that is the end of section 2.3, a pretty short one. I'll see you in section 2.4.